Okie dokie. So I think this lecture and probably the next two we'll all have together. As in all of us, I mean Chem 111 and Chem 131. And then after that, we will be splitting back up again to finish off the semester with a few separate topics. So today we will be pretty much talking about states of matter again, but this will be part 2. Last time we spoke about intermolecular forces, and just so you note, we could abbreviate intermolecular forces, I mean, as IMF. So that's what we talked about last time. So this time we will start with the idea of what is known as a phase transition. So phase transitions, what do I mean? I mean exactly as I sound. I mean by going from one state of matter to another. And so we will do solid, liquid, and gas. So the process of going from a solid to a liquid is known as melting. From a liquid to a gas is known as vaporization. From a liquid to a solid, freezing. And from a gas to a liquid, condensation. So, what is going on here? We have two types of energy I want to talk about. Kinetic energy and potential energy. These are the only types of energies that exist in the entire universe. And as you may have heard before, energy cannot be created or destroyed. That is another topic, but for today, all you have to know is what's going on is potential and kinetic are interchanging between one another. When energy is usually released in some way, it is being released in the form of kinetic being put into potential. And that potential energy has to go somewhere. And that potential energy is usually directed at something that absorbs that potential energy in the form of kinetic. So all we have is a back and forth motion of potential and kinetic energy. And so kinetic energy can be further defined as the energy of motion. And potential energy in another way. Well, this is more difficult to describe. The energy that is stored. And so this is usually the energy that is found within bonds. Also, as we might know, I didn't see the chat was open. I had it on a whole other screen and didn't notice. I have it in front of me now. But bond energy, so where was I? Potential energy equals the energy that is stored. We could refer to that as bond energy. And when we break bonds, how should I put this? Releases energy. How do I not know how to spell this? I always thought how it's spelled. L-E-A-S-A-S, energy. And forming bonds absorbs energy. Make sense so far? We can also describe energy absorption as an endothermic process. And we could describe energy emission or release as an exothermic process. And so energy release or heat. So when energy is absorbed or heat is absorbed and we feel it, we will feel cold. So an endothermic process will feel cold to us because it means that heat is being robbed or pulled away. An exothermic process, which is the release of energy or heat, will feel warm. So when we break bonds, we release energy or we release heat. When we create bonds, we absorb energy or we absorb heat. So this is the general trend of what's going on, and these are the words we will use to associate. I should make note that endo and exo, and also thermic. Thermic means heat related, endo means to absorb, exo means to release. So Now that we have these potential and kinetic energies pretty much handled, I want to talk about temperature. So, what is temperature? Well, when we add heat, almost perfect, to some molecules, we are going to increase the kinetic energy. And so this will mean increase in motion. And this relates to, as we increase heat, we will also increase average speed. And so I pretty much want to say here that temperature is approximately equivalent to the speed at which the molecules or atoms are vibrating. Slash moving. Because when we are in the solid state, the molecules can't really move around. They can only vibrate. But when we are in, say, the liquid or gaseous state, the molecules have more freedom to move around. So that's why I will say vibrate slash moving. So that is all temperature really is. So when we add heat to something, we are only increasing or decreasing the speed at which the molecules are moving. That is all that temperature is essentially related to. So now, let's see, where were we? Let us talk about a phase diagram. No, not a phase diagram. Let's talk about a cooling curve. So let's say we are going to look at water in this example. Make a nice box here. And let's put another shape inside here. Let's say this is temperature. And let's say this, how should I say, what is this? This will be energy. I will note that at some point I will redefine this to Q, but as for now, let's refer to this as energy in the forms of both kinetic and potential. Let us say this point on our chart is 0 degrees Celsius. And let us say that this point on our chart is 100 degrees Celsius. Let's make that a little nicer. So we will say that this is the heating and cooling curve for something that we all know, and that is H2O, or water. So we will begin to see a few trends here. Let's start our, actually, let us use a different color for our graph. What should we use? What should we use? What is a nice pretty color? Let's use green. Looks like it does not want me to use green because it's not letting me select it. I feel that I am the only person who has these problems with OneNote, and then just all of a sudden just randomly accepts it. But all right. So let's start our journey right at this point over here. So at this point right here, we are going to begin to pump energy into our water. And we will see that the energy will rise as well as the temperature. And at some point 0, we will see that the temperature actually stops rising, and we have to continue to pump energy into our water, which is interesting. So take note of this flat section on this curve right here. One moment. Then, after some time, we will notice we get all of a sudden a spike. And the temperature begins to rise again. And it rises, and it rises, and it rises, and it rises, and then it hits that magic number, 100 degrees Celsius, which we all know, or at least I hope we all know, is the boiling point of water. At this moment, we will note that the temperature stops, and we no longer increase temperature, even though we continue to pump energy into this solution. So we continue to pump energy, we continue to pump energy, we continue to pump energy, and at some point, probably right around here, bam, we notice that the temperature skyrockets up again, and it continues to go up like such. And here we have essentially our curve. And let me try to stretch this out proportionally. There we go. Right there. So here we have what is known as the heating curve for H2O. And now I want to define a bunch of points on this curve. And these are all super important points. So this first point exists over here. Let me actually change my color. Let's use white. chat. All right, so that is our first point, number 1. Here is going to be our next important point, number 2. Number 3 exists right here. Then we have 4. And finally, we have our 5th point right over here. So, in this state right here, in our state number 1, we have ice. Actually, let me try to. We have ice. Let's put it like this. So pretty much at any point below 0 degrees Celsius, water exists in its solid state, known as ice. As we are adding energy to this ice, we are increasing the kinetic energy of the molecules inside the ice. So say delta E is going to go up. Now that's what's going on at point number 1. So it makes sense. As we add energy, we are increasing the motion of the molecules of water. However, at some point, which is 0 degrees Celsius, that kinetic energy is going to stop increasing. And we are going to notice that something interesting is going to happen. We are going to have ice instead going to have an increase. Instead of kinetic energy, the potential energy is going to increase. So what does that mean? Let me actually shrink this a little bit. So what does that mean? Well, once water in its solid state reaches 0 degrees Celsius, we are going to begin to add energy instead to the bonds that exist between the individual water molecules. We are going to essentially increase the space between the individual water molecules until we break bonds. So, for example, this will be the hydrogen bond. So, during step number 2, we are going to increase the distance between the individual H2O molecules. Because think about it. When we go from a solid to a liquid and a liquid to a gas, we are essentially allowing a greater degree of freedom between the individual molecules, meaning they have to be able to move around more easily. And so they're going to need to separate more further apart from one another. And that means during this state number 2, instead increasing the speed at which the molecules are moving at, we are increasing the potential energy that is stored in the hydrogen bonds between the individual molecules. We could also think of it as the intermolecular forces. We are increasing the strain in those forces that once held the molecules together are now being pulled from one another. So that's what's going on during state number 2. Once we reach state number 3, we reach a new phase, and this will be, let's call, the liquid state. Water will be in its liquid state. And in this state, again, we notice that the temperature is increasing until we hit around 100 degrees Celsius. And just as we did before, we are going to increase the kinetic energy. Make that a little smaller. And the kinetic energy is the energy of motion. So during point 3, we are going to increase the speed at which these molecules are moving at. So they're going to start to vibrate faster and faster and faster and faster. And then at some point, which is point number 4, we are going to stop increasing that motion. And in the liquid state, we will say we will begin to increase the intermolecular strain or the potential energy. So, you should also take note that I actually drew this chart roughly to proportion. So it's interesting to note that the line that we see on step number 4 is much longer than the line in step number 2. And if you think about it, that somewhat makes sense. Because what is number 5? Well, number 5 is the gaseous state. And the gaseous state requires a huge amount of energy. So in the gaseous state, the ability to transfer from the liquid to the gaseous state requires a significant amount of energy to break the individual H2O molecules completely of those hydrogen bonds. So what is going on over here? How should I write this? Let me write this as there's our hydrogen bond. You could also refer to it as any intermolecular force. Specifically for water, we are talking about hydrogen bonding, but we could use this exact same diagram for any compound. And depending on the compound, we would substitute whatever intermolecular forces that compound has present. So what we have here is this will actually break. In order to transfer from the liquid state to the gaseous state, we need to actually break these hydrogen bonds or break these intermolecular forces completely. So this is why this line is so long. It requires a huge amount of energy to take water and convert it from the liquid into the gaseous state. I may have stated at some point before that the amount of energy to take water from the liquid state to the gaseous state, or rather from, I should state right here, let me put a marking on here. Let's use red. Let's put that. Let's put a point there. Let's put a point here. Let's put a point there. Let's put a point there. And I'm going to put a point right there. So, in order, back to white, this distance right here, I'm going to erase this because this looks ugly. And this distance right here, the amount of energy to bring water from 100 degrees Celsius at this point right here to its gaseous state, this point right here, is more than the total energy required to bring water from 0 degrees to 100 degrees. And I want you to think about that for a moment, because I'm all sure you've boiled water before on the stove. And you've watched it get really, really hot, and you'll notice maybe at some point you'll get very hot, but you still have not initiated boiling. We have to wait quite a bit of time, and then all of a sudden boiling will begin. And that is the reason why that it takes so long to boil water, because the energy required to break those intermolecular forces, to break those hydrogen bonds, is absolutely immense. And for water, it is the greatest of probably any compound that exists. And that is solely due to the fact that hydrogen bonding is one of the most powerful intermolecular forces that exist. Let me remove this. So there's a bunch of other things I want to say about this. There is a new constant. Let's see, I probably should have put it up here. Let's put it right down here. We're going to go back to the chart in a moment. We will refer to it as C. And C is known as specific heat. We also need to know the term, do I want to say this now or in a moment? Let's just do this, just specific heat right now. So what is specific heat? Well, specific heat is a measure of the energy required to essentially raise the temperature of a specific weight of compound. So specific heat is measured in the units of joules per grams kelvins per grams. Let me actually confirm this. Oh, I was right the first time. So it's joule gram kelvins. So what do we have here? We have a unit of energy divided by a unit of mass multiplied by a unit of temperature. So the specific heat is a property of individual compounds. So property of a compound. And specifically, it is the energy required to raise a certain mass of a compound a certain temperature. So obviously, the greater the number is, the more energy that compound is capable of absorbing before its temperature increases. So if we increase C, we will, how should I put this? How should I put this? How do I want to put this? We are going to increase the energy required to raise the temperature of the compound. So, as we increase the specific heat, or as a compound has a higher specific heat, that means it will require more energy to raise the compound's temperature. So let's go back to our chart. I want to state that specific heats are given during certain states. So during the delta E, we will use a specific heat, and we will use the specific heat of the liquid state. During this portion of the curve, portion number 5, let's say the delta K E is going to go up, and we will use the gaseous state. And let me actually, instead of ice, let's say solid, because that's more universal. All right. So at this, we will use the C of the gaseous state. And so let's look at what those are. We will, or I will, or not the gaseous state, the solid state. Oops. That of the solid state equals 2.10 joules per grams Kelvin. The liquid state is 4.18 joules per grams Kelvin, and the gaseous state is 1.97 joules per grams Kelvin. Now I want to make a note on this. We will notice that the steepness as well as the length of the curves are dependent on essentially what these values are. Notice how this value of 4.18 has a very long segment. This value of 2.10 has essentially nearly around half as long of a segment. And this value of 1.97 also has approximately around, well, actually, this actually will go up to a point where I'm not going to talk about it past this point. When we talk about phase transitions or phase diagrams, it'll be mentioned. But just note that the steepness or the slope of these lines are correlated to the specific heat values. Because note that we know that did not want to do that. The boiling point and the freezing point are both right here. So based on how we change the steepness or the slope of this curve will determine the height of this curve, or rather the length. Because if we were to make this very steep and, for instance, make it go up like this, it would be shorter. And we would have the phase transition occur right over here. For instance, if we were to make the slope super, super, super long, or super steep, or not steep, slanted, we would make the line super long. So it's actually the slope that these values are correlating to. Did I run out of undos? Yep, I ran out of undos. I'll leave that one there. What else? Do I want to mention something else about this? Let me think. So now I'm this section right here, section number 2 and section number 4. Section number 4 also have a value related to it, and this value is called the delta H of vaporization, and this value right here is called the delta H of fusion. So these have specific values. And do I have these values? Yes, I do. So the delta H of fusion is approximately 6 kilojoules per mole. And the delta H of vaporization is approximately 40.7 kilojoules per mole. You'll notice how this value is significantly larger than the value for fusion, and that is why this line is so much longer. This value correlates the energy that is required to strip or to break the intermolecular forces between the individual elements. This is why we are in the terms or the units of mole, and we have the units of kilojoules. So let me find a whole bunch of stuff right here. So enthalpy. Enthalpy is a measure of energy in a way, It is the unit H. How do I want to define enthalpy? Enthalpy is a bit tricky to define, and I don't want to so let's say, how should I define it? So we could define enthalpy as, let's say, the summation of thermal energy. So that's what we'll define enthalpy as for now. I will give a better relation to it for you guys in 131 when we talk about thermochemistry. As for you guys in Chem 111, this is probably the extent of what you need to know about enthalpy, and is essentially a measure of heat transfer. We could also state it as a measure of heat transfer. So that's what we'll define enthalpy as. I also want to make a note that this term right here, delta, means change. Whenever we see this, we could say that this means change. Therefore, we could say that delta H is equivalent to H initial minus H final. All this delta means is how the value of whatever you're placing in front of it has changed over time. That is all that delta term means. So whenever you see delta, that's what it means. Delta is used a lot. So make sure you make note of that. I also want to state that, I'm not going to write this down, but the reason why delta is used is because when we talk about energy and we talk about things in the nature of energy, we could never really quantify all the energy in the entire universe. So to say that we know this molecule has this much energy in it would be fallacious. It would be like saying that we know to the exact number how many grains of sand there are on Earth, or how many molecules of water exist in the ocean. It's just a task that is not logical, feasible, or even like possible to do. So instead of accounting for an exact value or a definite value, we measure the change in the value. Because if we know the value of something when we start and the value of something when we finish, we could definitely say something about that number, because we could for sure and with confidence measure the change in something. However, measuring the absolute value of something is not something that we could really do. And I feel the analogy of counting grains of sand really describes it. We can't say that there are X amount of molecules of water in the ocean, but we can say if I took a cup of water and poured it into the ocean, I added a cup of water to the ocean, and therefore I know the change, and therefore that is a quantity that has some meaning that is useful, and that is why we measure the change in values rather than the absolute values. So where am I? I want to continue talking about enthalpy. So that is what the delta means. I want to give you guys several different delta H's now. So we are going to have the delta H of fusion. We are going to have the delta H of, now this isn't one that's really used, but we could say melting is one thing we could say. It's not really used much, and usually we don't really refer to the inverse delta H's, but I want to just give you guys a term just so you can see where I'm going. So the next one will be the delta H of vaporization. And the next one and the last one is going to be the delta H of condensation. So the delta H of fusion, well, what is the delta H of fusion? Well, the delta H of fusion is the energy that is required to change a substance from the solid state to the liquid. And that's exactly what it is. So when we think about the delta H of fusion, it is the energy that is required to essentially melt something. Next, the delta H of melting, which we'll call, is nothing more than the negative delta H of fusion. So I abbreviated fusion as FUS, and you will usually see fusion abbreviated as such. So next we will talk about the delta H of vaporization. So the delta H of vaporization is the energy required. Actually, the definition is essentially the same as this one right here with one word changed. We're going to go from the liquid state to the gaseous state. So from the liquid state to the So when we talk about vaporization, that is what we are talking about. And in the same way for the delta H of melting, the delta H of condensation is equivalent to the negative delta H of vaporization, which I will abbreviate VAP. So, so far, any questions on any of that? Most of this stuff is all conceptual. Alrighty. Let's see. Say anything else about this? I think that's all I wanted to talk about this. So these are where these values come in. I think I hit every single value here. Enthalpy, enthalpy, enthalpy. All right. So one more thing. There are two equations that we are going to talk about. And these equations are Q equals MC delta T. And the other equation is Q equals N delta H, etc. So we'll say fusion slash vaporization. So how do I want to put this? Let's shrink this guy to right here. Put another one right here. And another one right here. So when we are talking about a compound and raising the temperature of a compound within a state, and by that I mean not jumping between state and such, we will mostly be talking about the liquid state. We will be using the equation Q equals MC delta T. When we are talking about changing the energy of a compound, such as a phase transition from a liquid to a solid, or a solid to a liquid, or a liquid to a gas, or a gas to a liquid, we will be talking about this equation, which is Q equals, so this one will go right here. Where should I put it? Right there. And this one will go here. Q equals N delta H of vaporization. So these are the equations. So this is a complete graph of everything. I know this looks cluttered, but we'll break everything down. So Q equals N delta H, and Q equals MC delta T. I want to use big T. So these are our two equations. Man, I'm really drawing at a slant. There we go. So Q equals MC delta T. So these are the two equations that you don't have to memorize. If I ever require you to do any equation on any quiz or exam for any class that you ever take me with, future or now, I will always give you equations. I don't feel people should memorize equations because anyone could be able to open up a book and pull an equation out. Your ability to use the equation is all that matters. So we will define the following terms. Since we defined the majority of the terms so far, we have Q is equivalent to heat. And this is equivalent essentially to thermal energy. N, which is the next term that you may or may not know, is the number of moles. So whenever you see a little n, and sometimes in some cases a big N, that term will almost always mean the number of moles of something. The next term that we probably have not seen yet is M, which may or may not know is equivalent to the mass. And depending on what your C is, it is usually in grams or kilograms. So at this point, we should have all of our terms defined. Yes? Are there any terms here that you need further explanation from? So C, we define C right here. So C is the specific heat. So specific heat is dependent on state and also is dependent on compound. So every compound has its own C value, and every compound also has a different C value depending on the liquid, solid, or gas state. Yep, T is temperature. So we could say T, temperature. And I'll define everything. We'll say C is specific heat. Alrighty. I don't want to say anything else about this. Okay, so you may or may not have to use these equations together or by themselves. If we are talking about just a change in temperature and not a change in state, so no change in state, we will just use Q equals MC, Jesus, delta T. So let's say we have a change in state. Let's say I'm asking if you're at 100 degrees Celsius, how much energy does it require to turn all that water, for instance, into gas? So change in state, no change in state. So change in state, we will be using Q equals N delta H to define one more thing. So let's say change in temperature and state. We are going to have to use Q equals MC delta T and Q equals N delta H, and we are going to have to find a big Q, which is the summation of all the little q's. So pretty much, if we are, say, for instance, for H2O, if we are going from, let's say, 20 degrees C to 50 degrees C. Let's say for H2O, 100 degrees C to gas. And for this, I would say for H2O, negative 20 degrees C to 150 degrees C. So these are the three types of questions that you could be asked about state change. You could be asked how much energy or heat is released or absorbed when we go from 20 degrees C to 50 degrees C for H2O. Notice how we have no state change here, because a state change will only occur pretty much from 0 degrees and below and 100 degrees and above. So as long as we're between 0 and 100, we have no state change, and therefore we only care about a change in kinetic energy, and so we only need the MC delta T equation. So 20 degrees Celsius to 50 degrees Celsius, Q equals MC delta T. Let's say we are at 100 degrees Celsius and we want to convert all that water that is at the boiling point but not yet boiling into a gas. We would use this equation, and we would plug in how many moles of water we have, and we would determine how much energy would be needed to be released or absorbed to convert that water into a gas. And finally, if you were asked a very complex question, which isn't too complex, of going from a temperature, let's say, of negative 20 degrees C to 150 degrees C, we would need to add multiple equations, get multiple Q values, and then add together all of our Q values to get a total Q value. And that will determine the total amount of heat that will either be released or absorbed by the entire process. So, I'm not going to do a problem with you guys today. We still have a bit more to talk about. I'm going to try to keep everything conceptual today. I think next week we will hit this again, but I will talk about more about the math behind this specific process. So we'll get some problems on this. Right now, I just want to talk about conceptual stuff for today. But other than that, do these equations more or less make sense? And does the process and idea behind it more or less make sense? So this right here is the cooling. Well, this is specifically the heating curve. The cooling curve would be the exact opposite. We would take this curve and literally just flip it around. It's the exact same thing. We just flip the curve around. So we would start at this point right here. If you could see my mouse moving around, this point right here would go on this point, and this point on the bottom would go on the right. We would just flip the curve around. So this right here is a cooling and heating curve. And these are, what did I just do? So sublimation, I'm about to talk about phase transitions in a moment, but sublimation is dependent on individual compounds, and it requires specifically the combination of temperature and pressure. So we'll talk about that right now, actually. These heating and cooling curves only apply to compounds that travel around the traditional route. And by that traditional route, I mean this process right here, from solid to liquid, liquid to gas, gas to liquid, liquid to solid. Condensation, or rather sublimation, and that process, it is going to be different than this. We're obviously going to have a curve that looks different. You do not have to worry about the cooling or heating curve in regards to sublimation, since that is a much more complex process. but I will show you guys something really neat, which is the phase transition or phase diagrams of compounds, which is really cool. So that is what we will talk about right now, actually. Phase diagrams. So a phase diagram is a diagram that pretty much explains or describes how a specific compound behaves under specific conditions of temperature and pressure. And there are three very specific points on the diagram that I want to point out. These points are known as the triple point, the critical point, and a supercritical fluid. All right. So give me one moment. Hold on. All right. So we have the triple point, we have the critical point, and the supercritical fluid. And you may or may not have heard of some of these terms before. So a triple point is the point where the solid, or rather, how about I say where the boundaries, no, that's not true, where the solid, liquid, and gaseous state are all observed. So at some point, or rather at some temperature and pressure, we are going to see that compounds will actually be able to take on the solid, liquid, and gas state simultaneously. And it is a very, very interesting thing to view. So if you've never seen or heard of it, you could definitely look it up on YouTube, where you will see a compound change rapidly between a solid, liquid, and gas because it is not able to really sit at any one specific state because the temperatures and pressures are at such a level that it causes the compound to behave as such. The next thing I want to talk is about the critical point, and the critical point is another very, very, very interesting point, and it's very useful as well. And the critical point is the point at which the boundaries of the solid and liquid phase cease to exist. So at some temperature and pressure, we will see a state change that causes the compound to reach a new state. And it is a combination of both the gaseous and liquid phase, not solid. So at this point, the compound will behave in a way that is very, very strange. It really has to be seen. I've actually thought about building a high pressure chamber to sort of to do experiments just to look at it. You need very, very strong steel tubing that is able to handle super high pressures. And you may or may not have heard of something known as supercritical CO2 extraction. And it uses the supercritical state, or a state past the critical point of the CO2 molecule, where CO2 no longer behaves as either a gas or a liquid, and it behaves as both of these states simultaneously. And what this allows the compound to do is it allows the compound to act as a liquid. And what does a liquid do? A liquid has the ability to salvate things. So think about like water, for instance. When we added substances to water, we were able to dissolve those substances in the water, and now the water was able to hold those substances. So in the supercritical state, we have these compounds able to dissolve things while still acting like a gas, which is insane, because by the ability to act like a gas means the compound now not only does it have the ability to salvate things, but it has the ability to permeate into things in a way that a liquid could not do. So when we have a compound in the supercritical state, that means it is in a state that is behaving as both a gas and a liquid simultaneously. And you could do very interesting things with it, such as extractions, because the supercritical state is allowing the compound to permeate into substances that a normal liquid would not be able to. And it also allows the compound to salvate those things that we want to essentially take in. So one of the ways that caffeine could be extracted from, for instance, coffee, is supercritical CO2 extraction. So when we take supercritical CO2 and pass it through coffee through it, we are able to take the caffeine and essentially wash it into the CO2, and then we take the CO2 away and we are left with coffee with no caffeine in it. And the supercritical CO2 works very well because it's able to permeate into the substance of the coffee better than most things. The alternate way of extracting caffeine from coffee is a solvent-based extraction, where you would use the compound known as dichloromethane. And it's actually a pretty neat experiment that if you guys ever took organic chemistry, it's actually a lab that I'd actually be interested in doing, because it's really, really fun, where you could take coffee and tea, and you essentially will soak it in a solvent such as dichloromethane, and the dichloromethane will, in a way, act just like how we want it to, and act as a solvent that will absorb the caffeine. And then we remove the dichloromethane, and we are left with the caffeine pulled from the coffee or the tea leaves. And as a result, we can decaffeinate things using dichloromethane. However, for the purposes of consumption, The use of supercritical CO2 is the preferred method because supercritical CO2 is totally non-toxic. And I don't know about you, I don't personally drink decaffeinated drinks, but if I did, I would prefer to drink a drink that had the caffeine removed through a process that leaves no traces and uses no harmful solvents rather than a process that uses a very toxic compound. Dichloromethane is super toxic and has the ability to actually leave trace amounts behind. So some coffees, I don't know about if they currently still do it, but some coffees are decaffeinated using a solvent-based approach, which uses dichloromethane or some similar solvent. And yeah, so we could use a solvent-based approach or a supercritical fluid-based approach. So I pretty much did not give you the definition of a supercritical fluid, but the definition of a supercritical fluid is any area in a phase diagram where the temperature and pressure are above the critical point. Alrighty. So that is what a supercritical fluid is. So a supercritical fluid actually has a very, how should I put this, large definition. Once we reach the critical point, we have converted our compound into a supercritical state. And as a result, if we raise the pressure or temperature in either direction, or rather increase it, we are still in this supercritical state, and therefore the region of increasing pressure or temperature above the critical point, we still maintain a supercritical fluid. So that is essentially just the definition of a supercritical fluid. So I want to make another notion right here, and I want to talk for a brief moment about pressure and temperature. So pressure. If we have a compound that is being represented by this dot right here, if we increase the pressure, what's going on is we are increasing the forces that are being applied to this dot or this compound. So as the pressure is going up, there is an inwards push to bring the molecules closer and closer together. And in the exact opposite way, when we look at temperature, there is an outwards push, because if you recall, I said that as we increase temperature, we increase the kinetic energy of the individual molecules. And what does that mean? That means we increase the motion of the molecules. So there's a back and forth fight between pressure and temperature. As we increased pressure, we could increase temperature to compensate. And as a result, the total energy of the system is going to continue to rise. So let me put this into words for you before I show you the first phase diagram. So we will say the greater the pressure, the more the molecules / atoms are forced together or pushed together. And the greater the temperature, the more the molecules slash atoms are pushed apart. So there's sort of a back and forth fight between pressure and temperature. That's the sort of trend I want you guys to get. So let us draw our first phase diagram. So that right there. Let's call this pressure. Let's put a whole box and a box around it to make it look all nice. So we'll call this pressure. Ooh, how am I going to draw this? No, I'm just gonna abbreviate it with P. So we'll call this pressure, and we'll call this temperature. So allow me to draw this diagram. So let's use, what's another pretty color we could use? Let's use blue. Ooh, it's too thick. So let's say right about there. So at this point, we are going to notice an important thing happening. This point. Let's actually let's change these to different colors. Let's change this to red. And let's change this to green. There we go. So I will say that the gas phase is here. Oops, we actually want to do something. There we go. Let's put this right here now. So All right. So this point right here is our critical point. This point right here is our triple point. So let's say this is the gas phase. We'll say this is the liquid phase. And this is the solid phase. So I want to make another note right here that pretty much every phase diagram, regardless of the compound, will look very similar to this. It will have lines that are just like this, and the lines will only just change slightly in slope or be more or less curved. We will see generally the exact same diagram regardless of our compound. So keep that in mind. So this curve right here that is red represents evaporation. So go back to white. / condensation. So if we are going from the gas phase to the liquid phase, we are condensating. And if we are going from the liquid phase to the gas phase, we are evaporating. So these are the two different phases, and this line represents the separation of those phases. This line represents melting and freezing. So if we go this way from solid to liquid, we are melting. And if we go this way, we are freezing. Now this line right here represents sublimation and, geez, what's the other word? It starts with a D. Deposition, there it is. So, here's my notes. If we go from a solid to a gas, this is sublimation. If we go from a gas to a solid, this is deposition. So here we have our essential entire plot. And I want to make another note right here. And pretty much anything you go through deposition and sublimation. So this phase diagram is stating that what I want you to, let me make this sublimation a little neater. Oh, I didn't want to do that. So So that's the critical point. The whole purpose of this phase diagram is to show you guys that we can modulate the temperature and pressures in such a way that we can make things behave differently. If we look at this phase diagram is one that is relative to essentially water. So on Earth, we are at some fixed pressure, and that pressure is probably right around here. So we'll say 1 atmosphere is approximately right there. So we will exist as some line on here. So what's going on is we are only changing temperature here on Earth, and therefore we cannot get water to sublime unless we change the pressure. So on Earth specifically, water will essentially go from a solid phase to a liquid phase to a gas phase following this line. Now, CO2, we will see, has an atmospheric pressure that is right around here. So, oh, why did it move? So CO2, we'll see, if it is existing in the solid state, as we raise the temperature, it will completely bypass the liquid state because the pressure is actually too low for it to turn into a liquid. And therefore, it will turn from a solid directly into a gas. So I think I'll maybe draw this image like 2 more times to show that on a less cluttered chart. There is one more area I want to note on this chart. Oh no, it looks like OneNote has decided it's going to start acting really weird. No, maybe not. So if that is the critical point, this zone right here is a supercritical fluid. I should note that we could call this T triple, or T, not triple, T critical. And we could call this point right here, let's call it P critical. So these points, or pressure and temperature, refer to the temperature and pressure at which we have a critical point. We could refer to this as the T triple. And we could refer to this as the P triple. So this would be the temperature and pressure that we achieve a triple point. So do I want to put anything else on this graph? I don't think I do. I mean, this is a nice graph. Are there any questions on this graph? Let's see. I'm gonna maybe go for like 5 or 10 more minutes and then we'll end it, because I just realized we actually have a chunk more to go, and I do not want to keep you guys for another hour, because I feel you are already at the point of being burnt out, perhaps. So let's take this. So now let me remove all this extra. So, because I said this is the general state of any phase diagram, this is essentially how they will look. But let me see if I can't look at. So this is the phase diagram of CO2 essentially has this point pulled up more. But we could essentially just state that we exist. So let's say this is CO2. And let's say we have 1 atmosphere right around here. And I should say that 1 atmosphere, ATM, is a measure of pressure, and it is specifically the measure of pressure that essentially is experienced on Earth. I want to note one more thing. This line right here is slightly different for the CO2 diagram. And instead of we go in that direction. So that's sort of how the CO2 diagram looks. So if we hold our temperature constant, we will see that we go across like such. So let's take this chart again. And let's say this is now H2O. This 1 atmosphere is probably right around here. And I should also note that line is slightly different. And I want to point something out, so let's use yellow. So phase transition, we only have 1 phase transition for CO2. So I just want to, let's see, maybe we could shrink these 2 charts and put them side by side. So I essentially want to note right here for you guys, when we look at these two charts, we see that CO2 will only have one phase transition, and this is sublimation deposition, while H2O will have two phase transitions, which is melting slash freezing and condensation slash fusion, or vaporization rather. So this is pretty much explained to us how and why we could have multiple phase transitions or change the phase transitions by modulating the temperature and pressure on one of these graphs. So we could force things into different states at different temperatures essentially by changing the pressure. Has everything I said so far made sense more or less? Any questions on these phase diagrams right here, or anything specifically we've talked about so far? Well, it's not necessarily elements, it could be compounds too. Like I said, or they can never hit. Well, we could pretty much force most things to hit the triple point. Some things may require incredibly high amounts of energy. Some things may not be able to reach the triple point specifically because the energy required to reach the triple point will cause the molecule itself to decompose. So some compounds we may not be able to reach the triple point, and that's just simply because the energy is just too much for the molecule to withstand. Compounds like H2O could pretty much take in huge amounts of energy, and therefore we don't need to really worry about any sort of decomposition of H2O or CO2 under super high pressures or temperatures. So some compounds cannot reach their triple point or their supercritical point, depending on several factors. What should I say? We can reach the triple point for a bunch of things. I'd say if you've never seen it before, you should check it out on YouTube. There's a bunch of really neat videos that show what it looks like, and sometimes it'll be inside a gas chamber, and you'll see the liquid or slash substance rapidly changing between a solid, liquid, and gas. It's pretty neat to see. And there's also some videos on supercritical fluids where you'll see when you move from the liquid state to the supercritical state, it's almost as the liquid all just turns into a gas and disappears. Sort of neat. Does that sort of answer your question? Any other questions on anything? If there are no questions, that is all I want to talk about today.